All right. Hello everyone. Welcome to the International Methods Colloquium. I'm Justin Essery, an Associate Professor of Politics and International Affairs at Wake Forest University. The International Methods Colloquium is a periodic online interactive seminar discussion on the application of quantitative statistical methodology to the social sciences, sponsored by Wake Forest University and previously sponsored by Rice University and the National Science Foundation. This week's speaker is Carlos Carvalho, Professor of Statistics at the UT Austin McCombs School of Business. His talk is entitled Bayesian Causal Forest, Exploration of Treatment Effect Heterogeneity. Carlos's talk will last between 30 to 40 minutes, after which point we will take questions from the audience. You can ask a question using the Zoom Q&A button that appears at the bottom of the webinar window. You may ask questions at any time during the talk, but all questions will be held until the end of the presentation. A link to Carlos's paper and slideshow will be available in the Zoom webinar chat window so that you may refer to it throughout the presentation, and I'll post those links right after this introduction is finished. And now I'd like to welcome Carlos Carvalho to the IMC. Welcome.
Thank you, Justin. Thanks for the opportunity to talk about our work. Let me just apologize. The titles of the slides that I have in front of me here are a little bit different, but it encompasses essentially the same thing that the title that I sent before was intended to convey. So this talk is going to be talking about Bayesian regression trees and focusing that effort on heterogeneous treatment effect estimation primarily. So this is joint work with Jared Murray, my colleague here at the University of Texas, Richard Hahn, my colleague at Arizona State University, and David Yeager, a psychologist here at the University of Texas as well. And there's a large number of people involved in the study that we're going to show you some results associated with that at the end of this talk. Okay, so what it is that we're trying to do here. I'm having trouble advancing my slides. Why is that? Okay, there we go. So just as a way of background and giving us a context for what we're going to be talking about, I'd like to talk about the space where we work these days called policy analytics, where it's just trying to basically emphasize the bridge between modern statistics, machine learning, and the use of those tools in causal inference, trying to understand how to really apply what we learned in the past 20, 30 years in statistics, machine learning to the field of social science, in particular focusing on policy questions. So, all of you that are in the social science space, you are used to see tables like this, right? Tables that throughout the last century we've populated a lot of our journals in a lot of different social science fields. So I pick one here. I like to joke that's an ancient result, and I use this example because it's written by my dean, so I like to poke fun of him. And this is a typical thing where, regardless of the name of these variables, don't worry about them, is that there's some outcome variable of interest. There's some treatment here that is perhaps is the top variable on this table, and we're trying to understand the causal effect of this top variable on the outcome. And we're controlling for a different set of covariates in different situations, and trying to suggest that, including fixed effects or not, under this controls or those controls, et cetera, we can claim victory because our coefficient estimate for the treatment effect is, pretty much the same with a similar standard error across a variety of different specifications. Problem is that we all know that this table is not a valid inferential table, in the sense that the choice of selecting the controls is a choice that doesn't come for free, and it has impact on, in particular, the magnitude of those standard errors that you see underneath the treatment effect estimates in the table. But we lived with those tables for a long time, and perhaps people will go from tables like this to try to explore now, okay, now let me try to introduce some interactions to see whether or not this particular treatment effect might change as a function of other variables that I might include in the model. So that's a typical thing that still it's done a lot these days. We started this work by trying to address this problem in the context of understanding how to select controls. So we're in this situation here. That was our sort of initial attempt in this literature, where we're interested in understanding alpha, the treatment effect. In this case here, the average treatment effect, impact of z onto y, controlling for x. And our interest was to understand how to select those x's in a way that does not impact in any bad way our estimates of alpha. So, imagine that you have a very large number of potential controls, and you're trying to figure out how to select or control for which ones you have to control for. This becomes not a predictive problem anymore, which it doesn't allow us to use the standard tools for variable selection. They are developed in the context of prediction, and it had to be adapted in a variety of different ways. So during that work that led to this paper that I cite over here, that was we identified a notion that we call, and it's going to be an important notion for what we're going to present here today, the notion of regularization induced cofounding. So this is a very important key term for what we're going to talk about today. So the idea is very simple. If I'm back to this equation here, again, something that we're all very familiar with. If I treat this problem as a prediction problem, I might end up, through the bias-variance trade-off, I might end up choosing to shrink the coefficients associated with some important control variables because they are not necessarily super predictive relative to other x variables of y. But the role in this regression is not a predictive role. The role in this regression is to hold fixed their variation in order to isolate the confounding that is associated with z. So by treating, again, using the standard tools out there, if I don't think about those tools carefully, it is very possible, and indeed happens quite often, for you to shrink away the importance of the controls associated with the x's, therefore biasing severely the estimates of alpha that you end up getting. So that's the sort of framework, the background here. So if I treat this problem as a prediction problem, I easily get biased estimates of alpha, my average treatment effect, in a linear regression, a linear sample model like this. Okay, so now let's start moving to what we're going to talk about today, which is to address the exact same problem in the context of nonlinear heterogeneous effect. So now I just changed my equation from a linear equation to a more general equation where I'm trying to understand now how this general function f, right, relates to y. And again, the notion now is that I have to be doing some sort of regularization, sort of prior control in order to get estimates of this function. And if I do that in ways that are not thoughtful, it's going to be, again, providing me with the same problem of regularization induced cofounders. That's going to be one of the main innovations of the work that I'm going to show you today, is to how to adapt predictive tools in this context here to allow us to do careful causal inference. All right, so we're going to provide a general framework for this particular setup. And we're going to try to focus today on the rich output that the models like this will provide us with and how to deal with that. Because the one of the nice things about linear regression is that the output is very straightforward to interpret. You look at your coefficient and that's it. It's your average effect. In nonlinear models, now you have all sorts of things at which you could look at. And we're going to try to focus on different strategies and try to evaluate and try to really gather a lot of the information that's available on that analysis. So let's go through the assumptions we have here. This is going to be, I'm going to be showing you examples in observational studies and experimental data. We're going to assume throughout conditional unconfoundedness or strong ignorability, which is to say that I'm assuming that I've measured all the plausible cofounders of the problem. So any factor causally influence the treatment and responses. And assume that I'm doing this, measuring a superset of X variables that may or may not be cofounders, may or may not be predictive of Y, and so on. So a big set of X's that might be my set of controls or predictors, really, that are important here. We're going to be thinking about heterogeneity in treatment effect as covariate dependent heterogeneity, meaning that individuals with different might respond differently to treatments, and that difference is going to be determined by some characteristics that I'm able to observe about those individuals. And finally, for today, which is not as almost without loss of generality, but there's some technicalities that we're still working on in advancing this. For now, we're going to be talking about binary treatments. Either you take the pill or you don't take the pill. This is not a dosage situation. You don't get the ability to think about dosages. All right, so there's a more formal definition of the assumptions that we have here. And two things that I'm going to highlight quickly here is that we need to assume positivity, which means that there's a positive probability that given the X's that we observe, one receives the treatment. That's an important thing. And we're going to be focusing on tau of X. This is going to be our estimate of interest, the conditional average treatment effect. So that's what we want to really focus on today, right? Which is the difference in expectation of Y for a given set of covariates X under the treatment, if Z equals 1, versus under the control when Z equals 0. this difference is the causal effect of z onto y holding x fixed, right? And this now is not just a constant, this is a function that depends on x. All right, so given that our object of interest that relies on that expectation, we're going to have to model that expectation. We're going to be coming through this as a statistical model, probabilistic model approach, which means that I'm going to be writing the expected value of y given x and z as a function of x and z. So that's what this statement here is, right? And our estimate then becomes the difference in the function f at z equals 1 minus at z equals 0 for a set of x's available for us. That's all to say that we're back to where we started here, where my outcome of interest is going to be modeled by a function of f, a function f of z and x plus some Gaussian errors. And again, this is for now it's what we're doing. This doesn't can be easily generalized to more general distributions in the error term. But let's assume additivity of errors and Gaussian errors for today. Again, the strong ignorability assumption is basically saying that there's a conditional independence between the error structure and the treatment given the covariates x. So the question then becomes, what do I do? What do I choose for f? Do I use polynomials? Do I use my do I use random forest? Do I use neural nets? Or do we use something that we understand and know how to regularize in in ways that are more manageable? So the real choice here, the real question that we're trying to answer is how do we choose how do we get to our estimates of f, and what's the prior really that we're going to be using to define those estimates? So I'm going to be proposing here the use of Bayesian trees, Bayesian regression trees, as a way to think about the problem, but not only regression trees in its basic format. So I'm putting in this slide here, what I'm showing you is a regression tree just demonstrating the principle of it, which is a tree structure T. We'll partition the covariate space here, example B here, x1, x3, into, let's say, 3 different regions, and it's going to fit a level function for y at mu h1 in this particular subregion, a level function mu h2 in this subregion, and a level function mu h3 in this subregion over here. And the subregion is defined by this regression tree, right? Where if I am above, if x1 is greater than c, then I am smaller than c, then I am in this bucket. And then if I'm jointly greater than c, smaller than c and smaller than d, then I am in this subregion here. So that's what you typically will be seeing in a regression tree. So that partition provides me with a step function in between the x's and y. So one tree we know for many years that tends to be a very coarse model. What we tend to do is do ensembles of trees. And the way we're going to do ensembles of trees here is through an additive ensemble of trees. So that's what's called the Bayesian additive regression trees. That's work by Chipman, George, and McCollum in 2008. It started actually much earlier than that. But the idea is that we're going to be representing f as a sum over trees. So each sort of like little piece of f is going to be estimated by a little small tree. So the idea is that I'm going to be combining a lot of small, short trees in order to get a complex function that hopefully estimates appropriately the f function that we're looking for here. So this is, in some ways, it could be considered state-of-the-art in the predictive world, in the Bayesian world, when I'm thinking about predicting continuous variables, thinking about estimating functions in this space. So that's something that has been incredibly successful in predictive tasks. Circa 2008, I think, and the paper actually appeared originally in 2011, Jennifer Hill of NYU proposed the adoption of this framework for causal inference. And the way she did that was by basically porting the ideas from this space here, basically taking that and applying to causal inference problems, where one of the covariates in here was z, the treatment, whether 1 or 0. And what we're going to show today here is that by using BART as a prior, and again, you might not never thought about the notion that I can think about this algorithm that was developed for prediction as a prior in my model. Basically, I have a prior for my f function, and that prior I'm calling the BART prior. The prior means that it's a very structured prior that has a lot of different knobs in it, and those knobs cut trees, make sure that to grow those trees in particular ways, and so on. Again, that part is very well understood in the literature, how to do that, how to control how to control for overfitting and all that, right? So in thinking about that as a prior, we can look at, well, are there problems in just going ahead and using a prior for f that is just BART, just the Bayesian additive regression trees? And what we're going to show is that in setups where we have strong cofounding, the estimates of individual or average treatment effects can be severely biased. Again, and that's due to regularization induced cofounding that I talked in the beginning. And two, if effects are heterogeneous but not high in their signal, BART can have a hard time nailing those things down, and it's going to be too variable in its answer. So we need a way to regularize more carefully our estimate of interest. When in a situation like this, without any modification, the estimate of interest is implicit in this parameterization. So we're going to be thinking about ways in which to isolate the estimate of interest in order to be able to exert direct control on its estimation process. So that's what we're going to do. We're going to address both of those points. So let me give an example of where regularization induced cofounding becomes an issue in this non-parametric model that we have here. So imagine that I'm measuring some sort of outcome, and the outcome is some measure of heart distress. So imagine that this being high, your heart's in trouble. This being low, your heart's okay. So Z is the pill that we're trying to understand the effect of it, and X1, X2 are some blood pressure measurements, something that you can measure on each patient. So we're going to generate some data from a data generating process. In this context here, in the following setup. So the setup is that, again, your measure of heart distress is going to be a function of a prognostic function of how your blood pressure basically tells you how that your heart actually works at the mu of X here. That's a part of the function that predicts directly Y. And then whether you take the pill or not, that will decrease the stress of your heart, because again, we're simulating data here with a homogeneous effect of 1 on Z. So if Z is 1, I get a negative, I lose 1 in my outcome here, right, on average. And if Z is 0, of course, I lose nothing. But the way we're simulating the data, we're saying that you are, the function mu of X is determined by if X1 is less than X2, you get 1 here. If X1 is greater than X2, you get -1. So your heart condition changes as a function of those blood pressure measurements. But the important part is that the way we're simulating, this is an observation study where we're saying that people who get the treatment, they get the treatment as a function of their prognostic. And again, that's something very typical in observation studies where you go to the doctor's going to prescribe you a pill if you're more likely to actually have the disease, right? You're more likely to potentially respond to that. So that's basically in this example here, we're saying that patients with X1 less than X2 are 5 times more likely to receive the new drug than the patient that did not. So imagine the situation where we're giving drugs to different people. People that get the drug are 5 times more likely people that have this characteristic here, which lines up very well with the prognostic function, are 5 times more likely to receive the drug than people that do not. That's a very low dimensional problem. There's a lot of signal here, the way we simulated this data. And yet, when you throw BART at something like this, you get very bad coverage for the average treatment effect here. We're talking about just the average treatment effect, because it's homogeneous in this case. And in a second, you're going to see that this is RMSE, and the bias is pretty high in this situation. And why is that? Well, it's going to be, again, because of the issue of regularization induced cofounding. What is happening is that the probability of one getting the treatment is a noisy function of mu. And so now the model is looking at two things. I look at Z and I look at mu of X. I'm trying to find out what mu of X is. Turns out that Z is a good proxy for mu of X. So by Z being a good proxy for mu of X, and if I look, go back here to this slide, a regression tree to find out mu of X is going to have to do a lot of different cuts in X1, X2 space because of the shape of this function here. And the tree models prefer, by the necessity to regularize those models, we prefer to make fewer cuts. We prefer to have short trees. And by preferring to have short trees, basically meaning that we have a strong desire to regularize, we're going to not like the idea of making a lot of those cuts. And it turns out I can avoid making those cuts by apportioning a lot of my function to Z, because Z is very much a function of, is very much similar to mu of X. So I can approximate mu of X by actually looking solely at Z and making a cut on that one-dimensional space, Z. And that's exactly what regularization induced cofounding is, by looking at two things and preferring to apportion the effect to Z because it's simpler, because I can do that with fewer cuts. I'm going to try to do that, and therefore inflating the treatment effect associated with this problem. How are we going to deal with this? we're going to basically estimate the propensity score ahead of time. We're going to estimate the propensity score ahead of time and use that as a covariate in our model. So it doesn't matter what you do here, as long as you have a good estimate of the propensity score. So the idea is that before doing anything, you figure out what is the probability of receiving the treatment as a function of the axis, and use that now as a covariate in your model. And what if we throw BART into that again? Now just use BART by adding one extra covariate, which is a one-dimensional summary representation of the axis, which again allows me now to look at Z and look at pi of X, and now separate, okay, what comes from pi of X, what comes from Z, and I'm going to avoid the problem of just unduly apportioning my outcome, really, the effect of the outcome onto Z and not pi of X. So when I do that, and I show you two versions of this here, one that uses the oracle in the situation where assumes knowledge of pi of X, and the other one that does a estimate of pi of X using an ensemble. And by conditioning those things, you see that my coverage jumps from 31% to 98 or 85%, depending on what you use. The RMSE gets cut by severe amounts, and the amount of bias, the bias, if you actually have this propensity score, your bias goes away essentially. And there's a little bit of bias left over in the situations where I have to estimate my propensity score. So that's lesson number one, is that regularization induced cofounding that we dealt in a linear model in a more prior-based way, because there was the linear model is a little easy to deal. In the nonlinear model, it comes up strongly. It can appear to be a strong problem that can be dealt with and can be severely reduced by the use of the propensity score as an extra covariate in your nonlinear, non-parametric estimation process. Problem number two is that treating the prior as a BART prior alone, even if you're adding the propensity score, like I have over here, right? This function is telling you that, okay, now I have my x's, I have my pi of x's, and I have my z. Even treating this, if I don't try to write this problem and focusing directly on the estimate of interest, I might end up getting a lot of variability in my estimates of the individual treatment effects, the ones that are the conditional average treatment effect that I'm interested in, because they are essentially, they're inside of this big function, but this big function is not necessarily focused on them directly. So the example that I have here, this little histogram in a simulation example that I'm not showing you this modification of the previous one, just shows you that if I make a modification onto BART, I'm going to get this tightly nice gray histogram over here. And if I use BART as it comes, even after adjusting the propensity score, I'm going to get estimates that have a huge amount of variance, as you see in pink. So we're going to be able to reduce the variability of the estimated individual treatment effects by reparametrizing my problem and focusing directly on the individual treatment effect. So how do we do that? We do that by rewriting the X function as, and that's what we call Bayesian causal forest in our work. We're rewriting the X function as a prognostic function, mu of X, that takes into account the propensity score. So here's, I'm basically taking all the X's that I observe and this one-dimensional summary of the X's that predicts Z, okay? That's the part that resolves the regularization induced cofounding problem. And separate now, so this surface here is a surface that tells me how X influenced the outcome. And this surface here is a surface now that is going to tell me about how as a function of X, how Z impacts the outcome as well, how Z actually how the treatment has an impact on the outcome. So I have two surfaces that I have to estimate now. So it seems it's harder in some ways, but it's not, because the way we're looking at this is our estimate of interest. That's what we want to do here, right? So I can put a BART prior on this piece of the problem. That's the prognostic function. But my interest is over here, which I'm also going to have a BART prior. But we can now exert very strong regularization on this function. I can make this function homogeneous if I want. I can make this a flat function, meaning that there's just one treatment effect of Z onto Y, just a constant. Or I can put a BART prior on this function, and in that BART prior, I can shrink severely towards homogeneity. What does that mean? Well, don't make a lot of cuts in your tree. Make it very expensive for the prior to allow a cut. And that's what we do. What we do is to say, all right, start with a model that allows you to find heterogeneity, but be very careful. Put a high bar on calling something a heterogeneous effect. Otherwise, you're going to be easily finding a lot of different things that are essentially noise. So put the bar high enough, and you're going to be protecting yourself against finding heterogeneous effects that are just not real. So that, again, is the reparametrization allows us to focus more directly on the estimate of interest. All right, so that's what we do, and there's some tweaks that needs to be done in order to implement this, but most of it is actually very straightforward. We have high probability for small trees or stumps on the tau function, again to emphasize this notion that we are encouraging homogeneous effects unless there's a clear evidence against it. And we have a few other modifications in the leaf parameters that are necessary for robustness of our estimates of tau. But that's details are not that important for today here. So there's a lot of computational machinery that goes behind our ability to run this. But again, we are taking not for granted, but we're borrowing a lot from the literature that has developed all these algorithms through the years and have explored very carefully the use of BART in a variety of different settings. We're just adapting it to the context that we have in place here. All right, so how does this do? This is the one time that I did not choose what simulation to show my audience when I write a model. This is going to be done basically independent from the choice of the modeler here. So the Atlantic Coast Causal Inference Conference has been organizing a data challenge since 2016, and it's basically trying to understand how these new tools work in a variety of different setups. They're done by a group of people, and then a large number of researchers across the country can submit their analysis, their methods to this group of people, and then they will crunch the numbers, then report the results on how well you'd estimated average treatment effects and conditional average treatment effects in a variety of different data generating processes. So this was I'm going to show you first the results from 2017, and then I'm going to revisit the results of 2016. So lots of different levers in the generation of these data sets. There were 32 different data sets with about 5,000 observations, 58 covariates in all of those. High noise, low noise, homoscedastic, heteroscedastic, additivity, no additivity, a lot of different things. And in each data set, there were 250 replicas of the data set. So you had to be doing well across multiple repetitions of the data set. So not only I didn't choose the data generating process to show you, I'm not even going to choose my competition either. My competition is going to be chosen by whomever supplied entries to that competition. So whomever thinks that they're developing methods out there that are useful for this space. So there's a paper written on this just to show these results. I'm going to highlight some of the results here that are important. What we found in these results is that across all homoscedastic data generating processes that were available that year, all BART-related work that takes into account the propensity score into its covariate space are the ones that are doing the best when thinking about coverage for, in this case here, the conditional average treatment effect. This is us over here. This is us, and this is basically us without the tweak on heterogeneity, right? So in this particular case here, averaging over everything, we've seen that the coverage is about the same for the conditional average treatment effects for BART, propensity score BART, or BCF, Bayesian causal forest. Meanwhile, again, with a very good interval. So we're doing that not at a cost of having very wide intervals. We're doing that with good power, right? We're achieving coverage at the same time and having good power. So we want to be in the very corner here, right? You want to be in the bottom of this plot. So our methods are essentially in the bottom of this plot, beating up a bunch of different choices of things out there. Linear model, for example, over here being very far away in the setup, right? I would like to draw attention to something that has been somewhat popular in this literature right now and has some theoretical guarantees and some papers being written on this, and in practice has shown to work very, very poorly in a variety of different contexts. And those are the causal random forests coming out of Stanford in the past few years. So this particular version here is what's called the gradient random forest that, again, theoretically has the correct coverage, but it doesn't seem to have it on a number of data sets that were available here, and it doesn't necessarily have very small intervals either. So we see that in coverage, and now let's look at root mean square error of the estimate, the estimates that we have in place here. So again, for conditional average treatment effects on the y-axis, and for the average treated on the treatment on the treated on the x-axis, and again, there we are. We're right here, very close to the other BART versions that use the propensity score. So these essentially are our methods down in the bottom where you want to be in this type of situation. And once again, the gradient random forest not doing so well. And it's not just in this example. This actually happened in a variety of different examples that people have looked at it in the 2016 challenge, the 2017 challenge, and the 2018 challenge as well. So that's the 2017, just In some other data sets here, those are the difficult homoscedastic data sets. Still, there's a little bit higher noise in this setup. Once again, the pattern is the same. We find our methods in the corner that we want to be here, high coverage, low, small intervals. And once again, when you look at the root mean square error in those data sets, we are at the corner that we want to do. So this is very encouraging that we're able to, at the same time, get good coverage on our estimates of interest and do that with low mean square error. So we're getting the right level of tests, if you want to think traditionally, with as much power as possible. After we presented our work at ACIC a few years back, the researchers that organized the 2016 context went back and reran that context with propensity score adjusted BART, and that's what ended up being the winner in that context as well. So this is a figure in that paper summarizing the results of the competition. So basically, we're very close to Oracle here when it comes to again, root mean square error and bias, so coverage and precision of the estimates. And this was a situation where we didn't actually submit. That was before our work was ready. So there's not much heterogeneity in these data sets here. So if you look at BCF versus just the propensity score adjusted BART, you get very similar results, which tends to be the case unless you have a very clear pattern of heterogeneity in your data. All right, so then let's revisit that one more time. We try BCF on the 2016 data to see how well we do, and we essentially just focus on the bottom table here. What I'm showing you here, that I'm doing a permutation-wise test on the difference between propensity score BART, which was the winner in 2016, and BCF, and basically we see that's the same. So the p-value here is pretty high, right? So there's no difference between PS BART and BCF on that 2016 data, given the amount of heterogeneity in the process. But important to highlight that both these methods are very different than BART, just BART, vanilla BART, or the causal random forest, again, that don't do very well. Again, the theoretically guaranteed coverage, it's just not there. Not in 2017, not in 2016, not in 2018. And again, BCF or propensity score BART are achieving the highest level of coverage at the lowest level of MSE in all those contexts. All right, so that's basically the takeaway here, is that by carefully adjusting our priors, by focusing on the estimate of interest that we have here, we're able to reduce the variability of our estimates, get more precise estimates of the conditional average treatment effect, and at the same time not have a lot of bias that would prevent us to have coverage in the situations. We're able to achieve both things. The way to do that is by focusing on estimates of the propensity score. I need to get a propensity score in order to mitigate this notion of regularization induced cofounding. And this notion can be applied to other non-parametric methods. You don't have to be focusing solely on BART. It could be something else, but you have to take seriously the estimation of the propensity score and using that in your model of choice here. Otherwise, the regularization that's going to be taking place in the non-parametric method is going to lead you to regularization induced cofounding very, very easily. We like our reparameterization to basically provides us with an extra focus on the estimate of interest and reduces the variability of our estimates in a lot of different situations. But what I think is most interesting to us here is the fact that it also facilitates the rewriting of our method in situations that are more interesting and more not just out of the box type of applications like the ones in those contests, but situations where we might actually want to take advantage of things like multi-level models. So what I'm going to show you now is just that, an extension of this work to the situation of multi-levels, which again, something that we do all the time in social sciences. So that's where my co-author David Yeager comes into place. He's the psychologist leading the effort on this national studies for learning mindsets. I don't have time here to explain to you exactly what this is, but it's a big educational randomized controlled trial that has been conducted in the past few years, where you intervene in students and trying to change their learning mindsets, whether or not they believe their brains are a muscle that can be worked out and get better as they go. So there's a lot of effort on this literature in psychology, educational psychology through the years. But this was the first study that really tried to do this at a national scale, representative sample, not like a convenience sample like most of the studies tend to be done. So this was done over 76 schools across the country. 14,000 students participated on this. The design of this study is actually incredibly well done. So it was designed in particular to explore heterogeneity. So they really cared about understanding mechanisms and trying to understand those mechanisms by finding heterogeneity in their study. There was a lot of pre-registration done, again, to avoid the issues of reproducibility and notions of finding spurious type of subgroup effects. And in that process of pre-registration, the researchers pre-register the notion that they would, after the fact that they test their subgroups that were pre-registered, they would provide a set of statisticians the data in a blind fashion, and allows us to explore with our methods subgroups and try to validate a little bit what they found and so on. So I'm going to show you a little bit of that. So a blinded exploration of the analysis of heterogeneity that we did in the end here. We're going to avoid this model selection specification search. We're going to be using one big non-parametric model and then trying to understand what that tells us. So we're going to fit one model here. There'll be one model, and then we're going to try to summarize that one model. But we actually are interested in know that we need to take into account school level effects that can be explained or unexplained by covariates. That's an important thing. And of course, school-specific effects that we know schools are very different, that have to be taken into account. So this is a situation where we clearly need a multi-level model. And the challenge was to figure out a way to adapt our non-parametric tool for a multi-level model like this. So here's a typical multi-level model linear that one would use in this situation, where the outcome of interest here for student I at school J would be GPA in this case, where we might have a school fixed effect or random effect, depending on what it will be, a school specific effect. We're gonna in the Bayesian world here, the distinction becomes a little silly, but so a school specific effect for alpha J. I might have some controls that are student specific and or school specific. These are linear terms here taking over those controls, where the betas being the coefficient associated with them. My student I in school J maybe got or did not get the treatment. That's Z over here. And Z gets multiplied by, well, a set of moderators now, a set of essentially interactions here between the treatment and some moderators of that treatment, right? Some student or school-specific potential modifiers of that treatment effect. That's where the heterogeneity is going to come from. That's heterogeneity explained by some things that I observe, but of course, I might allow for heterogeneity that's unexplained for things that I observe, and that's again basically protecting myself again against making calls that are associated with an X variable, but it really has to do with some school specific effect. So typical hierarchical model that one would fit here, and we're going to be able to adapt what we talked about in BCF, the Bayesian causal forest, very, very easily by basically modifying this function over here, which is a linear function, and this function over here by two nonlinear functions and the use of a BART prior. So here's how we write it, right? So exactly the same fashion, it's the same way that you write it, but now you have a non-parametric Bayesian prior for beta of X, the prognostic function of GPA as a function of covariates, and for the conditional average treatment effect, the one that's actually explained by covariates. So I explicitly change here X to W, because just to provide you with this notion that you can choose what goes into this function and what goes into this function. This was particularly important in the context of this research because some of the variables were pre-registered, meaning that there was a particular set of variables that were interested as a potential source of heterogeneity, and those were the W's over here. All right, so now fitting this is what I showed you before is essentially the same. There's a few different extra full conditions that you have to work out in this situation, but it's very trivial Bayesian update in fitting an MCMC on this. I gave you some reference already. I mentioned Jennifer Hill earlier on using BART in causal inference. I think the political science space, Green and Kern, have some adaptations of BART there as well. I should mention that. And in this case here, we're using the parameterization of BCF of Hunt, Carvalho, and Murray. That's the paper that originated this talk here. Okay, so basically just repeating some things that I already said. This allows us to have nonlinearities, interactions, etc. And once again, we're going to be able to exert strong control over the tau function by regularizing that towards homogeneity very, very strongly. Now, part of the challenge here is that we run this once, and you get a bunch of different stuff in your posterior. And there's a challenge of presenting this to the researchers or to anybody that's going to consume the analysis, right? So we're going to focus a little bit on that now here. So how do we summarize this? So one obvious thing to do is to roll up everything and focus on the average treatment effect. And that's the first thing I'm going to show you. And then we're going to do something that that we like to basically do a subgroup search that it's not going to give us any trouble in terms of finding specifications, because we're not going to be refitting any model. We're just going to looking at the results that we already achieved. And we're going to be doing some counterfactual treatment effect predictions, partial effects essentially associated with moderators in the end. Okay, so let's focus on the average treatment effect at first. So the average treatment effect, I'm showing you here the difference between what I would get from the linear model in light gray, that's the 95% confidence interval for the average treatment effect in the linear model, versus what I get from the multi-level BCF. And again, you see a very, very similar thing. On average, we're finding the same thing essentially, right? A little bit more shrunk towards zero in our case here because, again, we most likely because our model is so flexible that requires a lot of shrinkage. It shrinks everything down unless a little bit more than the high volatile OLS version, quote unquote, of this. So this is the scale of GPA. My co-authors tells me that this is actually a pretty large effect in this space. A lot of things in the educational space is going to be like in 0.19 or less than 0.25 at least. That's why this learning mindset literature is something that gets a lot of attention. All right, so what do we do in order to try to find subgroup effects? So what do we do here is that we're going to explore now our posterior means. We're going to look at the posterior means on the top function, the function that tells us about the treatment effects, and then try to figure out whether or not that can be approximated into buckets by a recursive partition algorithm like CART. So I'm fitting the fit. That's an old idea. I'm fitting the fit of the first model and breaking it down into, can I summarize that fit into, let's say, 3 buckets, 4 buckets, and so on, and then just looking at how much that costs me in terms of approximation error. So this can be formalized as a Bayesian estimate under a particular loss function in a nonlinear space. So I'm looking at my posterior and then picking a summary of that posterior. And that summary is going to be done on the piece of the model that matters for us, which is the conditional average treatment effect. So when we do that, what I'm showing you here is just basically breaking down that conditional, the posterior mean into 3 buckets. A bucket that is 2 of the moderators of interest were the ones associated with achievement for the students, how good that school is, and what are the norms in that school. Is that a school that students seek challenge or don't seek challenge? And again, I'm not going to have much time to tell you. I'm running out of time here. The details of this, but the idea, just what I want to show is for you is to say that in schools where I have a high level of achievement, in the top quartile level of achievement, what we're seeing is that I have a very low treatment effect from this intervention. So the intervention is not very effective if the school is already a very good school. On the other hand, in this bucket over here is a bucket where the schools are in the low end of achievement and are in the high end of norms. So that's a school that's not doing so well, but it's a school where students care about learning. That's basically what it is. And in that school, you get a very high treatment effect. The treatment effect that's on average is what? Something like 0.28. It is very different. It's close to 0.07 for the schools that are low achieving, but actually have students that seek challenges. That intervention works quite well. Meanwhile, in schools that the students are already doing so well, you don't see much of an effect. And again, if the norms are lower, that effect also is mitigated. Is not as strong, right? So I can show you also the posterior uncertainty of that here in this 3, basically breaking down the gray histogram here, the gray density estimate, which is done on everybody, on average, all the schools together, right? Once we do our point estimate, quote unquote here, point estimate of the top function into 3 groups, we're basically breaking down into the green group, the orange group that's here, and the blue group over there, right? So really, you're getting a lot of bang for your buck in this treatment by the schools in purple, the schools that are low achievement, but high norms. That's where you're seeing most of the treatment coming, but being successful here. So you can look, for example, at things like, whoa, is there a real difference between these two buckets over here? So I can roll it up, and in my posterior, everything is available. I can look at what is the probability of a difference between this group and this group. And again, you see something like this, a very high probability of a difference in the situation. There's lots of different ways to evaluate this, and just highlighting the richness of the output when you get to this setup here. If I wanted to do something else and go further, well, what if I want to break this group down into 2 groups here? See that what was orange here before? Can I further this down into 2 groups? And the answer is like, not really. You get now a probability of a difference much smaller, embedding 0 much more here. So the more you try to be specific, the less likely you're going to find a difference. And again, trying to find, that's the decision problem that you have in place here, is to stop, where do you want to stop on this? But remember, I'm not refitting my model. I fit my model once. I use the data once. I went from prior to posterior. Now I'm just trying to look at my posterior under different angles and trying to summarize that way. Final thing I'm going to show you here is the ability to do counterfactual predictions and understanding the effect of moderators. So what if we saw that schools that are so that we saw the schools there are so which ones that we're looking at? So how the estimate of treatment effects change in lower achieving schools if those schools were actually hold constant and would change their norms of those schools. What happens if we change the norms? If some schools were able to have high norms versus low norms, what would happen to their treatment effects? And that's what you're seeing over here. So we're basically trying to look at the original here is going to be, which one is the original? The groups are going to be, the gray ones, the ones in gray, right? The low norms versus the high norms in the dotted line. And now I'm just moving the norms up and down. And in the posterior, by picking the same set of covariates and just changing one of the moderators up or down, getting the estimates of the counterfactual treatment effect associated with that change. And that's what you see the movement here from the gray to the blue to the red, to green, which is the same and about the red. So if you move in norm space, you will be moving this much in treatment effect space as well. So again, a lot of flexibility in how we analyze things in the end. I'm running out of time, so I don't have much of a time to be specific about this example here. So just to conclude, in flexible models, variety of different flexible models available these days, with careful regularization and with your ability to think carefully about the posterior summarization provides you with a very large set of tools that seems to be a winning combination. We take the best parts of linear models and try to embed that into this nonlinear setup that we have here in order to allow us to understand really what are the pieces of the model that matter. So there's a lot of degrees of freedom in how we do this, and our parameterization is one that we can understand very carefully what it does, and it seems to be achieving very good degree of performance in a lot of different situations, not only in this applied setup that I showed in the end here, but in all type of simulation problems that have been explored so far. So with that, I'll conclude, and thank you.
Thanks, Carlos, for that presentation. At this point, Carlos Carvalho is available to take questions from the audience. You can ask a question using the Zoom Q&A button that appears at the bottom of your webinar window. And I'll get us started here. If I understand correctly, one of the main things you're doing is adding a propensity score estimate to a cart tree or a random forest in order to allow for confounding to be avoided, right, by excessive trimming of the tree.
Correct.
There's been in a different context, in the context of matching estimators, there's been some literature recently coming out of political science, but not just political science, that argues that propensity score matching is not advisable because it's too easy to misspecify the propensity score function. And it recommends essentially some sort of caliper-based quasi or coarsened exact matching instead, because it's sort of less bound by those parametric assumptions. And I'm wondering, in your case, if there's a potential for a similar problem of misspecification of the propensity score leading to residual bias.
Oh, it is. There's for sure, right? And you saw an example when I put this table here. In this table, you see that, so if I know exactly the propensity score, my bias is 0. Whereas if I don't, my bias is going to be larger. And I would defend that choice as like, well, sure, that's always going to be a case. But because I can do this offline, I can do this ahead of time, we can be very careful and try a bunch of different things, right? Really focus on that estimate, like that, because that's a prediction problem. That's what I'm trying to say. That's an easier problem because of the prediction problem. And we have all sorts of tools. So here we use an ensemble of different things. We can use our fancy latest version of a deep neural net to try to do something like that. It's a classification problem that we just have to treat it that way. And I think I have more hope that we're able to, with time and a variety of different tools available, get a much better a decent enough estimate of that, right? Now, if there's no, if there's two situations, right? One is that I'm perfect in estimating the propensity score because, or that becomes very close to Z. Well, that's the situation where there's nothing I can learn here. Or I'm in a situation where I cannot predict Z very well with X. Well, there's no cofounding then. And again, our estimates are only the bias, the bias of cofounding is what's going to come from that, right? In the matching literature, you're matching as a function of the propensity score, which is your estimates depend so dramatically on that I think the misspecifications there propagate themselves in a much stronger way than the way we're using here as a way to just try to avoid because with enough data, I don't need to do this. This is an issue of regularization. Mm-hmm. Okay, so and that's why I think we're more protected. Is the fact that we just need to nudge it away from this notion of shrinking the effect of the axis unduly, and then accidentally throwing things into Z.
If you didn't have to worry about moderators, which is going to make this complicated, another avenue I might suggest is thinking about instead of using the propensity score as a sort of it's not really pre-processing, but it's something you estimate before, to instead pre-process the data using some sort of quasi-exact matching algorithm, and then put that data through the causal forest. And from what I understand through the literature on really this is the literature on matching, that will be sort of doubly robust, right? So if the causal forest is valid, you'll get good answers and you'll avoid confounding. And then the pre-processing step is essentially doing what your propensity score step is doing. But it might do a little better. I think that falls apart because once you start to get into moderators, it's going to go nuts.
Right, and you're going to lose a lot of power.
Well, that too.
So that's the thing. And again, I really want to emphasize that taking the approach of matching, right? How do I do the problem that I showed you in the end? I think that the power of these tools that we have here, one is the fact that they seem to work out of the box really, really well, and that's an important thing. But I acknowledge that there'll be other tools. I can go and out of the box do something like do some matching, use some other versions of the causal random forest that have been proposed. That again, I haven't been able to make that work yet, but I can see that one making that work. But I think the power of our work comes in is by allowing us to write different probability models of it, showing you how to embed that into, let's say, a multi-level context and so on. Right? I think that's being very robust in estimating things in a generic sense, but also allowing flexibility to adapt and customize to specific situations, that the models that we typically like in social science and political science and so on.
I have another question about, this is specifically about the possibility for moderation. So you can show pretty easily that, for example, if you create a linear regression model and put a bunch of interaction terms in it, just a very basic form of moderation detection, it creates a multiple comparison problem because you're essentially allowing lots and lots of chances for dy dx to be big, right, by breaking it into a bunch of z categories. And it seems to me that the regularization, the sort of stronger regularization on the treatment effect stage, is sort of correcting for that. I wonder if it would get even stronger if you explicitly corrected for that using some, any one of the multiple comparison corrections that we know exist, essentially, accounting for the fact that there's going to be a greater possibility of detecting these things.
So that's a great question, and it's something that I would have to map, because remember, right, the prior here that says I don't like cuts in tall of x is what's protecting me, right? Saying, listen, you need to show me enough of movement in the likelihood for me to make a cut.
Which is going to get you, that's going to prevent you from making this mistake horribly. Yeah.
Making a map between that in tree space to what we understand in the multiple comparison space, which is done in multiple testing. Those are much simpler settings, right? It's a little tough.
That's why you get paid the big bucks.
Exactly. Our view is that, from a philosophical point of view, I actually don't necessarily like the thinking in the multiple comparisons setup. I much prefer, and I've been doing work on this for the past few years in the linear models, where I prefer to work with a supermodel. and make sure that I try to regularize the model as much as possible, and just to understand how my predictions behave as a function of that. And then if model interest in some variables is interest in variables is something that I care about, understanding coefficients, if partial effects, and so on, then I try to do that as a posterior summarization step. So I'm thinking about that as a Bayesian estimate under a certain loss function. Why do I want to summarize the model? Well, because I need to talk in 3 dimensions. Okay, if you need to talk in 3 dimensions, what's your best 3-dimensional representation of the posterior? That's how I tend to think about these problems these days, because all the nice theoretical and good type of results that we have in the multiple testing things, it just doesn't port to the situations of more complex non-parametric models that we have.
Yeah, and I think the connection of your model is really more to these sort of Bayesian combinations of models with weights by the base factor, right? So you're essentially, allowing for uncertainty and specification, and that's the sort of you're coming at it. Seems like you're coming at it more from that perspective than the perspective of individual level testing of effects.
Correct.
I had one other question. What did I thought I wrote it down. Maybe I didn't. Where did I? So I want to make sure I understand exactly what's happening, particularly in your last example, in your applied example. So it seems like what you're doing, if I understood this correctly, is you're estimating a Bayesian causal forest with a blunt treatment effect, and then taking predictions from that model for the treatment effect, and then trying to model those sizes with X. So it's really a 2-stage process. Is that right?
So let me go back to the slide here. So I'm fitting this model here in slide 31. Okay, this model gives me draws of everything, right? My posterior explorations procedure here gives me draws of everything in this model. One of the things that I get draws of is this thing over here. Okay, so I can get, for every iteration of my MCMC, I have a draw for tau of W, right? Which I can then take, let's say, the posterior mean of the function. So I have a function now,
right?
Okay, so I have a function, and in a few dimensions, right? But that function now, it's my posterior mean, okay? So under a loss function of interest, I would say report that posterior mean. That's what I would report, right? But now I want to say, no, I don't want to report that function. I want to now summarize that function. I want to report something else. I want to report my best 3-bucket approximation of the function. And that's what we do over here. Okay. For example, if I want to report the best 3-bucket approximation of this function, feeding in the x's. So now I have almost like a new prediction problem. I have my posterior mean, and I'm trying to now predict the posterior mean as a function of the x's. And the x's in this case are continuous 2-dimension, the 2 x's of interest here in this example. And I'm just trying to figure out where to cut, right? What are the cuts that I can make that would separate them in a meaningful way? So in other words, take that thing that if I look at the average, my uncertainty is dictated by this gray density here, and now find me the best cuts in the space that's dictated by achievement and norms, and where those things are most different. And that's what you get in the green, red, and blue. Now, it is 2-stage in a sense, but it's 2-stage without using the data again. I didn't use the data again. That's my estimate. That's my posterior mean. I'm just now looking at the posterior mean under a certain lens, right? I'm just now choosing a Bayesian estimator, right, as a way to report my results. And that's a very important distinction, because if I go in and I tweak the moderators and run it again, I tweak the moderators and run it again, that's when you start getting into the what's Gelman's
p-hacking, garden of forking paths.
There we go. So we're not. So my forking paths here are on the object that the data told me about this object already. Done, right? I'm just trying to see if I can slice and dice this object after the fact in a summarization step.
Well, it's 1:00, so I'm going to go ahead and call the seminar. I'd like to thank Carlos Carvalho for being our presenter this week. I want to point out that his presentation will be posted to our website shortly after this broadcast if you'd like to share it or with a colleague or watch it again later. I also need to announce this is the last IMC presentation for academic year 2018-2019. I want to thank all our presenters for being a part of a very successful Colloquium series this year. If you wish to rewatch any of the talks given, they're available for you for viewing at please contact me at justin@justnecessary.com, or you can see our website, which is again www.methods-colloquium.com. Carlos, thanks for giving the talk this week.
Thank you so much for the opportunity. It was fun.
And I hope to see everyone next year.